So an antiderivative of a function little f of x is any function capital F of x such that little f is the derivative of capital F. So the game we usually play is that typically when we're given little f, we usually ask for f prime. Now, instead of asking for the derivative of little f, what we're doing is we're treating little f as a derivative. We're saying little f is itself the derivative of some function capital F. And so now our question is, what is this function capital F? It's known as the antiderivative of little f. So this is similar to derivatives, but we're sort of working on the reverse problem. I'm not trying to find the derivative of f. I'm trying to find a function whose derivative equals f. And so to do antiderivatives, it's really, really important that we can do differentiation well. We're literally learning how to do derivatives forwards and backwards. So I have a really easy kind of toy problem here just to get our mind used to the game that we're playing. Because what happens at this stage, it's kind of natural to get slightly disoriented and sometimes be not sure whether you're taking a derivative or an antiderivative. So this is an easy example, as I said, it said to find the antiderivative of x squared. So first of all, let's think about what we're trying to do here. I'm trying to find some function capital F such that the derivative of capital F will equal x squared. And so I'm going to do this by trial and error. For example, I know that the derivative of x cubed is 3x squared, and the derivative of x cubed has the x squared part that I want, but it has this 3 in the front that I don't want. But I can actually get rid of that 3 using properties of derivatives. So here, 3x squared, as you know, is the derivative of x cubed. Now what I want to do is divide both sides by 3. Since 3 is a constant, we can just divide both sides by 3. I get x squared is equal to 1/3 times the derivative of x cubed. And now my final little trick here is to take the 1/3 and bring it inside the derivative. We know that the derivative of a constant times a function is the same as the constant times the derivative of the function. So here I bring the 1/3 in, and now we notice that we're able to write x squared as the derivative of this function 1/3 x cubed. And so 1/3 x cubed, we claim here, is an antiderivative of x squared. And we can check the answer. We can always check our antiderivatives by differentiating. The derivative of 1/3 x cubed should be x squared. And certainly it is. The derivative of 1/3 x cubed is 1/3 times 3x squared, and the 1/3 and the 3 cancel, and we get back x squared. So here I used a phrase here. I say it's an antiderivative. That is to imply that this is only one antiderivative and that there are many more. So in fact, this function 1/3 x cubed plus c, where c can be any real number, this function would be what we call the most general antiderivative. So the most general antiderivative. And here, this function, f of x equal to 1/3 x cubed plus c, that doesn't represent one function, that represents infinitely many functions. For each choice of c, we have a different antiderivative of x squared, technically speaking. And we can check this, here's one lesson, is that we can always check our antiderivatives by differentiating. Here, if I take the derivative of 1/3 x cubed plus c, I should get back x squared if I'm claiming it's the antiderivative of x squared. Certainly when we take the derivative, we get 1/3 times 3x squared plus 0, 0 being the derivative of a constant, and the 1/3 and the 3 cancel, and so we get back x squared, which is our function little f. So here, this is kind of an example of the game now that we're going to play when we're doing antiderivatives. We're now, kind of going in the opposite direction. So here I wanted to write down this result that the antiderivative of a function isn't just one function, that it's a whole bunch of functions. It's what we call a family of functions. So here, suppose capital F of x is an antiderivative of little f of x, or another way to say that is suppose the derivative of capital F of x equals little f of x, then the most general antiderivative of little f of x is this, what we call family of functions f of x plus c. So here, since c can be any real number, f of x plus c for each choice of c will technically be a different function. And we have some notation here. And so this part's really important for the notation. We write, if the derivative of capital F is little f, or if the antiderivative of little f is capital F, then we use this notation here. This symbol, we can call it the integral symbol for now. So as of right now, in the story that we're telling, we haven't introduced an integral yet. Okay, we will introduce an integral this week. And then in the theory, the antiderivatives and the integrals aren't necessarily related, but then the mean value theorem will relate the two. So right now we're studying antiderivatives, pretending like it doesn't necessarily have anything to do with integrals. Then we'll study integrals, and then we'll connect the two using the mean value theorem. So this statement here, I would read this sentence. So I'm reading from left to right. I would read this as the antiderivative of little f of x dx is equal to capital F of x plus c. And when we write this statement, what we're really saying, and this is really important, is when we write this notation, what we're really saying is that the derivative here of the right-hand side equals little f. That's really what we're saying. It's really important that you interpret this notation as saying something about the derivative of capital F. And so I've written this here. So I say the antiderivative of little f is equal to f of x plus c if and only if the derivative of capital F equals little f. Or here you can say if and only if the derivative of capital F plus c. I didn't include the plus c because we know the derivative of a constant is 0. So when you see this statement in your mind, what you want to verify is you want to check, is the derivative of this part, is the derivative of the f of x plus c part, is that equal to little f? If it is, then we have a true statement. That's the only time we can write antiderivative of little f equals capital F plus c, is when the derivative of capital F is equal to little f. By the way, this constant here that we add, that's known, that has a name. It's called a constant of integration. So when we're doing antiderivatives, we're going to be looking for you to write down the plus c and to not forget that part. It kind of seems silly at this point in Calc 1, but in differential equations, these plus c's will make a difference and will be important. So it's really important that we develop good habits now, for later. So here are some basic anti-differentiation formulas. These are essentially our derivative rules that we're just running backwards. And we'll check these rules by doing differentiation. So here's the most basic one here. So start by just focusing on this rule right here. We say the antiderivative of 1 dx equals x plus c. So what I'm actually saying is the derivative of x plus c equals 1. And I need to say, is that true? Yes, the derivative of x plus c with respect to x is 1 plus 0. So that's a true statement. And more generally, so now if you look at the second statement here, more generally, the integral of k dx, where k is some constant, is kx plus c. Again, we should interpret this as a derivative statement. The question we're asking is the derivative of kx plus c with respect to x, is that equal to k? And yes, the answer is yes. Certainly the derivative of kx plus c is k times 1 plus 0. So this is a true statement that we're checking with derivatives. This is why being able to do the differentiation is really important. The dx part just tells us which variable is in play and which variable I should take the derivative with respect to. For example, if this said integral of 1 dy, if this was a y instead of an x, then the answer here would be y plus c. And I would check by taking the derivative of the right-hand side with respect to y, and you'd get back 1. So don't worry about the dx and dy for now, but it typically tells us what's the active variable, what's the variable we're working in. It becomes a little more relevant in Calc 3 when we end up working in more than one variable. In Calc 1, it's not as important, but it is important to develop good habits, so it's important to write down the dx. So this is called the power rule, not for derivatives, but for antiderivatives, for integration. Okay, so for any number n not equal to -1, and I'll talk about that in a second, we have the following anti-differentiation rule, that the antiderivative of x to the n is equal to x to the n plus 1 divided by n plus 1 plus c. So let's verify that this is true. What I'm going to do is we're going to think about the derivative of x to the n plus 1 over n plus 1 plus c. Remember, n plus 1 is a constant. So when you take the derivative, it's a power rule. The n plus 1 comes down times, I have x to the n plus 1 minus 1 would just be n. Here I'll say n plus 1 minus 1 divided by n plus 1. And so you can see the n plus 1 in the denominator cancels with the n plus 1 we brought down. And in the exponent here, the plus 1 and the minus 1 cancel. So I just end up with x to the n. So that's what we're looking for. So then we can claim that the antiderivative of x to the n is x to the n plus 1 over n plus 1 plus c. So what about this n not equal to -1 business? So when n is equal to -1, we're trying to find the following integral. So when n is equal to -1, we're trying to find the integral of 1 over x dx. And in fact, in this third portion of calculus, when we're talking about integrals, there's also a mystery. And so the mystery is, what is the antiderivative of 1 over x? That's a mystery that we will resolve in chapter 5, okay? And spoiler alert, it turns out that the antiderivative of 1 over x dx, we will never actually find an antiderivative. What we'll end up doing is creating or engineering a solution to what's the antiderivative of 1 over x dx, okay? But that'll happen in chapter 5. So don't worry about the antiderivative of 1 over x, until chapter 5, and we'll talk about it then. Using the derivatives of sine and cosine, we have the following antidifferentiation formulas. The antiderivative of cosine is sine of x plus c. Again, the way we verify that this is a true statement is we ask ourselves, what's the derivative of sine of x plus c? The derivative of sine of x plus c is cosine plus 0 or just cosine, and that's exactly what we're looking for. We're looking for the derivative of this term to equal this term. And then, this will be a true statement then. I can write the antiderivative of cosine equals sine of x plus c. And similarly here, the antiderivative of sine of x dx equals negative cosine of x plus c. Remember, the derivative of cosine by itself is negative sine. So here the antiderivative of sine would have to be negative cosine, because the derivative of negative cosine would be negative sine or just sine. So it's really important that you are, to verify a statement like this, you are thinking about what's the derivative here of the right-hand side, and is it equal to this function here that we're trying to find the antiderivative of. In this case, of course, the answer is yes. So these are more general properties. This is similar to when we say the derivative of the sum of two functions is the sum of the derivatives. This is basically saying the same thing. This is saying the antiderivative of the sum or difference of two functions will be equal to the sum or difference of the antiderivatives of each function. This basically says we can find an antiderivative of a sum or difference piece by piece. I can look at the first part in the sum and find the antiderivative and then move to the next piece, just like we do a derivative, just piece by piece. And similarly for constants, we have this rule that the derivative of a constant times a function is equal to the constant times the derivative of the function. We have the same rule for antiderivatives. The antiderivative of a constant times a function is equal to the constant times the antiderivative. Basically, what we're imagining is we're able to pull the constant out of the antiderivative, calculate the antiderivative of the function, and then multiply back in the constant. That's what that's saying. And I wanted to show you a quick proof of those last two. I'm reluctant to just give you the formulas and ask you to memorize them. These proofs are a little subtle. You don't need to know the proofs. You do need to know these properties. So the proofs are not difficult, but if you're not used to doing proofs, it's, we're using logic here, and sometimes it's a little weird if you're not used to logic. So sorry, I think I accidentally muted myself there for a second. So here I'm going to let capital F be the antiderivative of little f. So exactly what does that mean? I'm saying f prime equals little f. Or another way to say that is, if we use our notation here, another way to say that is let this whole thing here equal capital F. Another way to think about that is what we're saying is the derivative of capital F equals little f. And then I say let the antiderivative of little g be capital G. And again, another way to think about that statement is another way to say that exact statement, let capital G be the antiderivative of little g, is the derivative of capital G equals little g. Okay, so now let's look at f plus g. We can write it as f prime, capital F prime plus capital G prime, because, we said capital F was the antiderivative of little f. So capital F prime equals G. And here, G is the antiderivative of little g. So capital G prime equals little g. Now we use properties of the derivative. We know the sum of the derivatives is the derivative of the sum. Okay, so at this stage, you should think about what we've shown, and you can kind of ignore this middle step here. At this stage, we've proved that capital F plus G is the antiderivative of little f plus g. And another way to write that is with this notation. Remember, let me remind you, we can only write this if the derivative of the right-hand side equals this thing in here, the thing we're trying to find the antiderivative of. And this equation proves exactly that. This equation up here proves exactly that the derivative of capital F plus G equals little f plus g. So that's a true statement. And so the final step is, remember, capital F actually equals this antiderivative, because we said capital F is the antiderivative of little g, and we said capital G is the antiderivative of little g. So I can replace F and G with their antiderivative notation. So like I said, this is a little weird. There's some logic going on here. If it feels or looks weird, that's normal. And don't worry about it. You're not responsible for proofs. You are responsible for knowing the result. And having said that, let me drag you through another proof. So here I want to prove that the antiderivative of a constant times a function is equal to the constant times the antiderivative of the function. As before, let me assume capital F is the antiderivative of little f. Another way to write that is to say capital F equals, and then this integral symbol, little f dx. This is the same. And another way to write that is to say capital F prime equals little f of x. These are all the same thing. These three things in these three boxes are all the same. They all are the same. They're all equivalent. You know, saying f of x is the antiderivative of little f of x is the same as writing this f equals integral f of x dx is the same as saying, you know, the derivative of capital F equals little f. That part is one of the most important things I can get across to you, you know, that I'm just repeating over and over again to get that connection. So here, I now want to say something about 2 times f of x. Okay, so I'm assuming little f of x equals the derivative of capital F of x. So now let me say something about 2 times f of x. 2 times f of x equals 2 times capital F prime, because little f equals capital F prime by assumption. And now, property of the derivative, I can bring the 2 inside the derivative. So what I've shown is that the derivative of 2 times capital F is 2 times little f. So another way to write that is the antiderivative of 2f of x dx equals 2 times capital F. But remember, capital F is actually this integral. So when I replace capital F with that integral, we get back our property. Again, it's a little bit, there's logic involved here. You know, it's the type of math that's really math. You know, math isn't just plugging and chugging and putting in numbers. That kind of math ends kind of after Calc 3, differential equations, that kind of math ends. And then we start to do more logic-based math, like in matrix methods or linear algebra. So if it looks a little weird, that's fine. Don't worry about it. You know, you're definitely not responsible for proofs, but you should know the results. Now, this next example, this is the type of problem you absolutely need to be able to do. So this next example, this is something we absolutely need to follow all the steps and make sure we understand, you know, how to break this down. So we're asked to find the antiderivative of this function, cube root of x plus 5 over x to the 6th. So it's really important that we understand which direction we're going in. It's, you know, I see a very common mistake where students will now at this stage take a derivative. And that's not what we want to do, right? We're trying to find a function whose derivative is this given function here. So we kind of want to go backwards. So I'm going to use the properties of antiderivatives. First, the antiderivative of cube root of x plus 5 over x to the 6th. I rewrite this in x to the n type form because I have a rule for the antiderivative of x to the n. Cube root of x I can write as x to the 1/3. A 5 over x to the 6th I can write as 5 times x to the negative 6th. And so now I'm going to split this up into 2 antiderivatives. The antiderivative of the sum is the sum of the antiderivatives. And then I also pulled out this constant. The 5 was in here in front of the x to the negative 6th, but it's a property of the antiderivative that we can, first of all, the antiderivative of the sum is the sum of the antiderivatives, and then the antiderivative of a constant times the function is equal to the constant times the antiderivative of the function. So that's what we've done here. Break up the sum and pull out any constants. So now I want to find the antiderivative of this expression and the antiderivative of x to the negative 6, and then multiply that by 5. So here, as I said, we have a rule for the antiderivative of x to the n, you know, this so-called power rule for antiderivatives. The antiderivative of x to the n is x to the n plus 1 divided by n plus 1. Remember, at this stage, I want you to, in your mind, go, okay, what we're saying is that the derivative of x to the n plus 1 over n plus 1 equals x to the n. And that's a true statement, and you should check that, and you should verify that. So now I'm going to use this formula on this antiderivative with n equal to 1/3, and I'm going to use it on this antiderivative here with n equal to negative 6. So we're going to use the same formula twice but the n will be different in each case. So here's my antiderivative of x to the 1/3. And for this antiderivative, I got a constant of integration. So don't forget, when you do an antiderivative, you then want to slap on a plus c. Here I called it plus c1. Why? Because I have two antiderivatives. When I do this second antiderivative here, I get a second constant of integration here, which I'm calling c2. CU Boulder alert just got sent out. I don't know. And then we add the two constants together and just call it C. So I don't expect you to write a constant of integration for every antiderivative. I don't expect you to write this one. You know, you can just combine them already right when you do the antiderivative and just write plus C. But you should understand what's going on when you do decide to skip that one step. That for each antiderivative, technically speaking, we get a constant of integration, technically speaking. So from this first integral, I got a constant of integration. From the second integral, I got a constant of integration. Constant plus constant is just another constant that I call C. So here, C is C1 plus C2. Okay, so here, this is C1 plus C2. But as I said, I don't expect you to be so explicit and write a constant of integration for each antiderivative, but I do want you to understand what's going on, right? So, you know, and so here's my, final answer here. So I just now need to do some algebraic simplification. So if you look at this first expression, we have this fraction in the denominator. So I can pull the fraction out and multiply and flip it over. So here you can multiply x to the 4/3 by the reciprocal of 4/3. With the other term, this 5 down here will cancel with the 5 up here. This x to the -5th, that should be in the denominator. And then we'll have this minus sign. Okay, so here I have x to the 4/3 times the reciprocal of 4/3, which is 3/4, minus 1 over x to the 5th plus c. And so here's my final answer for the antiderivative of the cube root of x plus 5 over x to the 6th. Here the properties are important, being able to break it up, being able to write this as x to the n, and then using the appropriate antiderivative. And then simplify, and don't forget the plus c, don't forget to simplify. So we're going to be looking for the plus c. As I said, it becomes important later in math and life. So here's another problem that's kind of very standard that you should be able to do, that we can do right now, okay? So some of this problem we're going to simplify, and some we're going to think about, can I just guess the antiderivative? So for example, when I look at negative cosecant cotangent, that seems very familiar to me. And so if I review my derivatives, if I'm not mistaken, the derivative of cosecant is negative cosecant cotangent. So right away, I already know the antiderivative of this part. I still need to think about, okay, how do I find the antiderivative of cosine times tangent, and how do I find the antiderivative of 1 over secant? Okay, so here, for cosine times tangent, we can simplify that. I know that tangent is actually sine over cosine. So cosine times tangent, we can actually cancel this cosine and just replace the whole thing with sine. And secant, as you know, secant is 1 over cosine. So 1 over secant will be 1 over cosine, or just cosine. So here, after simplifying the first and the last term, we're looking for the antiderivative of sine of x. So the cosine tan just becomes sine of x, minus cosecant cotangent. I just copied that down because I know the antiderivative of that already. And then I have minus 1 over secant. The 1 over secant I simplified a cosine. Now that it's in this simplified form, I'm going to try and divide and conquer. Let's look at each piece separately and see if we can't find the antiderivative. So here, for this first function, the antiderivative of sine of x, I'm thinking, you know, what function, when you take its derivative, gives you sine of x? It's negative cosine of x, right? The derivative of cosine is negative sine. The derivative of negative cosine is negative negative sine, or just sine. So the antiderivative of sine will be cosine. Here for the second term, I brought the minus inside because I know from having memorized my derivatives that the derivative of cosecant is negative cosecant cotangent. So I know the antiderivative of this entire term I can just replace with cosecant. Finally, I ask myself, what's the antiderivative of cosine? I know the derivative of sine is cosine, so here I have, you know, the pieces here. So here, antiderivative of sine, antiderivative of negative cosecant cotangent. My apologies, in the slides I sent out, I had a typo and I wrote cotangent here. And that was before I followed my own advice of reviewing my derivatives. And so I had a cotangent here, and the cotangent in the slides I sent you, that's wrong. It should in fact be cosecant. So after I reviewed my derivatives, I look back at this slide and I go, wait a minute, there's a mistake here. That cotangent should be a cosecant. So this proves that, not that I'm human, but that I'm a machine that's not working properly. So I'll have to go in for a tune-up at some point, you know, whatever. And then here's the derivative of the cosine part, which is sine. Now notice here I've copied down the minus sign, so don't forget this minus sign here that I've copied down is right here. And the final thing I want to point out is I wrote a plus c. At the end, we find the antiderivative of each piece and then slap on a plus c when you're doing an antiderivative. And be careful, I had a typo in the slides I sent you. I wrote, instead of cosecant here, I wrote cotangent, which is incorrect. This, instead of cotangent, it should be cosecant. And I apologize for that. And I'll re-upload these slides a little bit later today. And so, yeah, so here's my final conclusion, is that the antiderivative of, you know, cosine times tangent minus cosecant times cotangent minus 1 over secant is cosecant minus cotangent minus sine plus c. Again, in your slides, you might have a cotangent here, but that's wrong. It should be a cosecant. Okay, so I had a typo in these two places in the slides I sent you. So I'll go in for a tune-up and get that, you know, addressed. So yeah. So here, this problem, I like this problem. It's not difficult, but it's a conceptual problem, and there's kind of a trap here that sometimes students fall for. So that's why I wanted to do this problem. So suppose capital F of x equals the antiderivative of secant of x dx, and suppose f of 0 equals 1. We're asked to find the equation of the tangent line to the function capital F of x at x equal to 0. So, you know, throughout this entire semester in calculus, we're always going to be doing equation of the tangent line. And here we are talking about antiderivatives, but still there's an equation of the tangent line problem. So remember, we're looking for this equation. The equation of the tangent line of capital F at 0 would just be, you know, capital F of A plus capital F prime of A times x minus A, where here A is 0. So if you look at the pieces, I'm given F of 0. We're told F of 0 equals 1. The piece that's missing is F prime of 0. I need to figure out what is F prime of 0, because we have F of 0, x minus 0 is, you know, that's just x. I need to figure out F prime of 0. So here's the big mistake that students sometimes do, and what I want you to avoid. Students will sometimes try and calculate this antiderivative. Here, it's important to understand from a conceptual point of view that we don't need to actually calculate the antiderivative. So if you keep in mind, I know f of 0, I need f prime of 0, but to find f prime, I don't need to necessarily know f. I just need to take the derivative of f. And when we write this notation, capital F of x equals the antiderivative of secant of x dx, that's another way of telling you what the derivative of capital F is, right? We only write this notation if the derivative of capital F here will equal secant of x. So when they tell us f of x is the antiderivative of the secant of x, they're also actually telling us what the derivative of capital F is. Because remember, I'm going to just mention it again, just to bug you. When we write capital F equals integral of secant of x dx, what we actually mean is that the derivative of this thing here on the left-hand side has to equal the thing we're trying to find the antiderivative of. So this statement tells us the derivative. This tells us the function value at 1. So all I need to do is evaluate the derivative at 0. So I'm going to plug in a 0 for x. And secant of 0 is 1 over cosine of 0. Cosine of 0 is 1. So secant of 0 is just 1. And so now I can plug in all the pieces. So the equation of the tangent line, f of 0 is 1. F prime of 0 is 1. X minus 0 is x. So the equation will be 1 plus 1 times x, or just y equals 1 plus x. So not a difficult problem, but we have to be careful of falling into the temptation of trying to find the antiderivative of secant. It's not necessary in this problem. Also, we won't actually learn what the antiderivative of secant is until chapter 5. Okay, so this problem, to me is not a difficult problem, but it's conceptual and potentially tricky. So I want to end up here. Last couple of slides here is to, just like we applied derivatives to rectilinear motion, and we were able to, from the position function, get the velocity function and acceleration function. Now we want to go backwards. Starting from the acceleration function, I want to take antiderivatives and find formulas for the velocity function and position function. So this is probably something I should have done a month ago that would have helped you in physics. You've probably seen this by now. But starting with our acceleration due to gravity, negative 9.8 meters per second squared, keeping in mind that the acceleration is the derivative of the velocity. So another way to say the acceleration is the derivative of the velocity is that the velocity is the antiderivative of the acceleration. And so here the game we're playing is that we know the acceleration and we don't know anything else. And we'd like to find the velocity and position function. And so we know, using our antidifferentiation theory, that if v prime equals the acceleration, then the velocity will equal the antiderivative of the acceleration. And so here, the velocity will equal the antiderivative of negative 9.8. Pay attention now here, t. T is the active variable here. So before we said the integral of k dx, where k was a constant, is k times x plus c. So if you say the integral of k dt will be kt plus c. Okay, so here the constant k is negative 9.8. So the antiderivative of negative 9.8 with respect to t is negative 9.8 t, and then don't forget to slap on the plus c. And I can check that this is correct. I can take the derivative of negative 9.8 t plus c with respect to the t variable, and I get back negative 9.8. So that's how I know that's correct. And suppose the initial velocity when t equals 0 is equal to v sub 0. So we've just introduced some new notation that's called v sub 0 or v naught, and that just represents the velocity at time 0. And so here, if I plug in t equal to 0 in my formula for the velocity, I get that that constant of integration is actually the initial velocity. So I can write the velocity formula in this fashion. V of t equals negative 9.8 t plus the initial velocity. You know, you should appreciate this from the point of view that suppose I only knew the acceleration. Using calculus, I'm now able to come up with a formula for the velocity. You know, and that's novel. That's getting some information from very little information. And we can take this one more step, right? We know the velocity is the derivative of the position function. And as I said, another way to say the velocity is the derivative of the position function is that the position function is the antiderivative of the velocity. So if I know the velocity, in theory, by taking the antiderivative of the velocity, I should be able to find the position. So here, s prime of t equal to v of t, that's exactly the same as saying s of t equals the integral of v of t. And now we go in and do the antiderivative piece by piece. So the negative 9.8, we just copy. It's a constant. What we're doing is we're taking the antiderivative of t. So here, you know, let's think this all the way through. Here, this is t to the first power. And so when you do the antiderivative, the rule is you go n plus 1 divided by n plus 1. So here I get the antiderivative would be t squared over 2. And so that's what's written over here. I copied down the constant, negative 9.8 times t squared over 2. For the v sub 0, this is a constant. So the integral of v sub 0 dt is just v sub 0 t. And then finally, you know, don't forget to slap down your plus c. Here I called it c tilde because technically speaking, I already used the variable c for something else. So I didn't want to use the variable c for, you know, two different purposes. It's not that big a deal, but you know, I'm a math nut, so I like to follow these little things. But yeah, technically it's a different constant of integration because we've done a second integration. So I just call it c tilde. But anyway, if we get this position function here, and if we assume the initial position at time t equal to 0 is s sub 0, then with initial velocity v sub 0 and initial velocity, initial position s sub 0, we can write down our full position function. And I know, you know, this is nothing special. You've seen it in your physics class tons of times, but you should appreciate that with just knowing the acceleration, we can come up with the position function. So for example, you know, when we're trying to land the rover on Mars, based on knowing the gravitational pull of Mars, we're able to write down the position function and velocity function, you know, and then track its position as it's being lowered to the surface. So that's kind of, even though it's a simple thing, that's, you know, a very powerful application. And of course, there are many, many applications. If we take the acceleration in feet per second squared, you know, it's negative 32 feet per second squared, then the position function after two integrations, after two antidifferentiations, will look like negative 16 t squared plus v sub 0 t plus s sub 0. Oh, here, I forgot to mention here, I did this division here, negative 9.8 divided by 2. That's where the 4.9 came from. That's why this 32 becomes a 16, because we divide by 2. So here I just have a little toy problem to end the section today. So a ball is dropped from a tower 450 meters above the ground. We're asked to find the position of the ball at any time t. So I assume that this ball is dropped from a tower 450 meters above the ground on the planet Earth. So the problem didn't actually specify that it was on the planet Earth. So I'm going to assume it's on planet Earth. I'm going to assume acceleration due to gravity is negative 9.8 meters per second squared. And then I'm going to integrate twice, right? And the work for that was on the previous slide. And by doing 2 anti-differentiations, we get the formula for the position. So all I need now is the initial velocity of the ball and the initial position of the ball, the position at time t equal to 0. And so, you know, since the ball was dropped, the initial velocity is 0. And since the tower is 450 meters high, the position of the ball at time t equal to 0 is 450 meters. So my initial position is 450. So now I'm in business. I just have to substitute the v sub 0, you know, for the, I should just substitute the initial velocity and the initial position, and then we have our function. So v sub 0 will go in for my initial velocity, and then I substitute for my initial position here, and so we get 0 times t, negative 4.9 t squared, plus 0 times t plus 450, and so I simplify here to just my final answer, which is negative 4.9 t squared plus 450. So, you know, we will be doing this procedure many, many times. For you right now, it's to really understand the concept of an antiderivative, you know, and how differentiation plays a role in this. We're literally learning how to do derivatives backwards and forwards. So it's incredibly important that we really make sure we know our differentiation rules. That's what's going to be make it possible for us to do anti-differentiation. And then when we use mean value theorem to connect up antiderivatives and integrals, we'll be able to do integrals, you know, provided we understand all of our derivative rules and can do differentiation really well. All right, folks, I'm going to stop right here. That's my time for today. Thank you.